Got to press record. Homework questions. So we got moved on to chapter 8. Chapter 8 was comparing two samples. The hypothesis that you see on page 349 is for one sample. The hypothesis for two samples pretty much says the same thing, but instead of comparing one mean to population value, now we're comparing two means to population values. Okay. And there is this thing about pooling. Did I explain enough about pooling? Yes, pool your data. No, do not pool your data. How do you know? If variances are equal, say yes, pool data. If variances are not equal, which is most likely the case, I recommend personally to not pool data ever, because it's very, very unrealistic for standard deviations to be equal. If the population means are not equal, then the standard deviations are not going to be equal unless it comes from the same population. Okay. So this is 8.1, 8.2, we're looking at means of two variable data. I like a couple of the questions where they ask you for or give you the data, and then you got to compare those two samples. For example, tensile strength on page 433. I like the question. I don't recall if I assigned problem number 19. There's an experimental method and an old method. They measured the tensile strength for two different things there. Is there a difference between those two things? If there is a difference, then we're going to use the new method. If that works. If there's not a difference, we're going to stick with the old method. Why are we going to change everything? Okay, see if it works. See if it works. If it works, then we'll use it. Yeah, another thing that happens in education, textbook adoption. Usually, this is what happens when we get a new book. One person likes the book, and they have a lot of influence. Therefore, everyone's going to use the book. Well, the best way to do it would be to collect some data on what students' opinions are about the book. Do a course using the new book, and everybody uses the old book. We have the old and the new. Get people's opinions about both, students' opinions, not teachers' opinions. And then, hey, did they score better using the new book or the old book? Look at test scores, look at people's opinions, look at data, collect a lot of data about things and compare those two sets of results. There it is, teaching methods. Page problem number 21 on page 434. Is one teaching method better than another teaching method? Teachers, like athletic trainers, think they're the best teacher in the world, right? So some teachers are like, yeah, I'm really good at what I do, and all my students love me, and I'm really smart, and my method is the best. I've been in teaching for 20 years, and I've never met a teacher that was like, I need to get better. I'm just not very good. Never heard that. I say that. I'm like, what are you doing? What are you doing? I'm trying to pick everyone's brains. I want to get better. But using a teaching method, look at the data. Is one teaching method better than another? A lot of times grades are used. Well, there's that grade inflation that I was talking about. Some teachers inflate their grades. And I look at data, and that's what I do in one of my jobs. I have another job where I look at data and I analyze the data. And there are teachers that inflate their grades. And they're giving a lot of A's and B's compared to the average of everyone, right? So I'm like, what's going on here? Then I dig deeper into their data and find other things like, one homework assignment for an entire semester, stuff like that. I see some crazy stuff. Anyways, that's a good question there. Problem 21, teaching methods. Is one teaching method better than another? Should we use that teaching method? Does it work? Okay. Any questions? Page 424, page 432. So you might notice that we're continuing 8.2. So I did 8.1 and 8.2. Talked about it. Planning to see about two samples. It went really fast because we did the test. I didn't know if we'd have enough time or the quiz. That's why I did 8.1 and 8.2, and then today's 8.2 and 8.3. And tomorrow we're only doing 8.4 by on its own. Okay, so we're kind of continuing 8.2 right now. And I put 8.2 and 8.3 together because 8.2 is sampling, comparing two samples. So two sample testing. And this is the title of 8.2. Two sample testing for independent samples. If samples are independent of each other. 8.3, the title for 8.3 is two sample testing when samples are dependent. So as I mentioned, when you're doing a clinical trial, you're trying to find the cure for cancer. We're gonna have 40 people get chemotherapy. We're gonna have 40 people take a pill and get chemotherapy. Did those 40 people that took the pill, did they improve faster or more significantly than the group that didn't take the pill, that were not in the clinical trial? If there's a difference, then we're gonna be like, hey, the pill works. Eureka, I'm gonna sell this to everyone in the world and I'm gonna be a billionaire, right? That's independent samples. I have two completely different groups. Okay, if you can imagine, here's the line. There's one group, there's the other group. So those samples are independent because we have different people that don't know each other. They all got pancreatic cancer. I'm going to try to help them. Okay, I'm going to work with them. It's called clinical trial, and it happens every day in the United States. So I got independent samples. Well, what's a dependent sample? That is when one person does two different things. Or I take two people of the same, with the same, maybe the same gender, same height, same weight, same stage 2 cancer. I put them into two different groups and measure their results. Okay, a matched pairs experiment, or a what's called a paired experiment, where I'm going to do two different things. Okay, that's more likely. So I'm going to do chemotherapy for 6 months. No improvement. Then I'm going to do chemotherapy for another 6 months, but then now I'm going to be in a clinical trial. I'm going to take this experimental pill. Then I'm going to compare the two results. Did I do better with the pill and chemotherapy, or did I do better when I only took chemotherapy? Okay, which one helped me the most? Okay, that's a dependent statistical test. Okay, so we're going to learn about in 8.3 testing when you have dependent samples. So this is called a paired experiment. And in this experiment, it's just a control and a treatment group, control group and a treatment group. Okay, you just have two groups. There's no connection between the two groups at all. They're just going to do different things. As long as you randomly assign people in the different groups, you'll be fine. That's kind of the difference between those tests. So we're going to learn about those tests today. We're going to do a lab today. It's not going to be hard unless you don't know how to make a paper airplane. I got a paper right here. Everyone's going to pull a paper airplane and we're going to throw them and see which airplane goes further. Okay, so it should be pretty fun unless you've never made a paper airplane before. We're going to do this as a few sample tests for independent groups. So I'm going to have two groups. They're going to be independent groups. We're going to see which airplane goes farther. We're going to take data and measure the difference, called a two sample t-test. Because I don't know the standard deviation. If you don't know standard deviation, you're going to do a t-test. Then you're going to fold both airplanes. So after you do your first airplane and it goes 3 feet, don't crumble it up and throw it away. We're going to keep it because then we're going to go on and do a paper airplane test for dependent samples. So then you're going to fold two airplanes. You're going to throw both of them and see which one goes farther and measure the difference to see if there is a difference. That's a dependent test because you are gonna do two different things. And we're gonna measure that difference. If there is a difference, if there's no difference, we would get 0. For example, I folded one, it goes 6 feet. I fold another, it goes 6 feet. The difference is 0. That means there's no difference. Okay, but we're gonna measure everybody's, not just one airplane. We're gonna measure a bunch of them. All right, so I have all the paper here. I'm gonna give everybody 2 sheets of paper because for right now, you're only gonna use one of them. Do not start folding until I give you I'm gonna assign you, I'm gonna randomly assign you to one of the 2 groups. Okay. I'm gonna give everybody 2 sheets of paper. It might take me a few minutes. And let's see here, we got Sarah, Isabella, Sarah, and Martha. If you guys want to fold paper airplanes, just do an 8.5 by 11 sheet of paper. And you're gonna have to measure how far it goes. Let's just do one right. All right, again, I'll tell you how to fold. I'm gonna give you folding instructions. It'll be like an origami. So may know how to make the origami. Pretty cool. Really cool paper designs. All right, at this point, I usually show a video. You guys want to see the video of the world record paper airplane flight? I'll just tell you how it's folded. It's a long, skinny paper airplane. So the first fold goes like this. This is a hot dog fold. Don't fold your paper airplane yet. Okay, I'm just telling you what the world record looks like. The ones that start off with a fold this way, the long, skinny one, actually, the world record, we think that those are going to go farther. Okay, the ones that fold this way, we call them a hamburger fold. Probably not going to go as far. So that's our hypothesis. So I'm going to write the hypothesis first before we start even folding anything, before we even collect data. When you first see the question, remember, we read the question, and then we're going to try to answer the question. That's the goal. Again, going back to the quiz, some people didn't answer the question. They just said, oh, reject HO. Well, what's the answer to the question? So here we go. If your airplane looks like this is going to be number 1. This is the hot dog team, or I like to call them the engineers, because they're going to go far. If your paper airplane looks like this is number 2, and you're going to be the hamburger team. Actually, I'm not going to call them hot dogs. I'm going to call them dogs. Because I need 2 different letters. I got D for dogs and H for hamburgers. Okay. So again, I think these are going to go farther because the world record airplane looks kind of like this. Okay. So we're going to collect data and we're going to measure the distance that they fly. So I got my hypothesis. Do hot dogs fly farther than hamburgers? That is the question. So we're in step 1. We're going to follow a 3-step process. I'm going to write my hypothesis. Is mu1 less than or equal to mu2? Is mu1 greater than mu2? The distance, we're measuring a mean distance. So again, mu1 is the dogs, the average distance of all hot dog folded airplanes. This is going to be the hamburgers. And again, you could use letters right here. The 1s and the 2s, I could put D for dog and H for hamburger if I wanted to. That's a good way to label your data. So I'm going to tell you at home, don't fold your airplane yet. I'm going to tell you who's who. So I'm going to give you a number. You're a 1 or a 2. Okay. It's going to be pretty easy. Are you ready? 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2. 1, 2, 1, 2, 1, your first fold, if I gave you a 1, your first fold is going to be in half long ways. If I gave you a 2, your first fold is going to be a hamburger. The next thing you want to do after that is you want to make some kind of fold like this to make wings. You're going to fold it down. If you fold it like this, you're going to fold it somehow like that to make wings. You're going to make wings for your airplane. Let's see here. Sarah and Isabella, you guys are going to be 1s. If you want to participate, you don't have to. Martha and Sarah, you're going to be 2s. And you're going to fold your airplane. And you're going to throw your airplane. Our runway, our airport is in the hallway, is where we're going to throw our airplanes. So I'm going to meet you in the hallway to throw the airplane. Either there is evidence that the long, skinny paper airplanes go farther than the hamburgers, right? The short ones. That data is looking pretty good right now to me. Don't you think so? In order to figure out if there's a difference, we're going to find the mean of both of these. So in order to find out if there's a difference, I'm going to find a z-score if I know standard deviation. We don't know standard deviation, therefore I'm going to find a t-score. Our population variance is equal. Okay, this is about standard deviation. The standard deviation of all of those airplanes, is the standard deviation going to be the same as that one? Probably not. Even looking at sample standard deviation, I think these numbers are more spread out than those numbers. They're a lot different. So that's the assumption we make. The standard deviations are not equal. Therefore, the variances are not going to be equal. So I'm not going to pool my data. No pooling. If I'm not going to pool my data, I'm going to use the standard formula. T-score. Once we get a T-score, then we could get a P-value. But ultimately, we can rely on our calculator. That's the formula for a T-test for 2-sample statistics. I'm going to do this on my calculator. We have data. We have the hypothesis, step 1. In step 2, it was pretty cool. Some people just did this on the quiz. In step 2, we just wrote P and P-value. That's all I'm really looking for. And P-value tells me there's a difference. Well, we need to find the mean, and we're going to compare those. X bar 1 and S1 and 1. X bar 2, S2 and 2. Let's compare those statistics. I don't have my calculator. I must have left it in my hotel room. I don't know. It was over there somewhere else. I know I use it. Is the mean of these airplanes bigger than the mean of those airplanes? I'm pretty sure it is, but is it significant? Do these go significantly further than those? Okay, so what I want to do is have somebody enter the data, put this in the list 1, because it's number 1. Put this data in the list 2. We cannot do 2 variable stats. 2 variable stats only works if the sample sizes are the same. And these sample sizes are the same, so I guess we can do a 2 variable statistics. So how do you get to 2 variable stats? We enter data, list 1, list 2, and then we go to stat, go to calc, and number 1 is 1 variable stats. Number 2 is 2 variable stats. Anybody get the 2 variable stats yet? Thank you. Thank you. Got those numbers up there, you can verify. Two variable stats only works if sample sizes are the same. If these numbers were different, which is mostly the case, then we can't do two variable, we just do one variable stats for list one, and then do one variable stats for list two to get our statistics. Like I said, these numbers have more spread. Those numbers are more spread out. There's small numbers, there's really big numbers. I knew the standard deviation was going to be much bigger. There's more spread. Look at the mean, 6.8 feet on average, 4.1 feet on average. So we're saying, is this number bigger than that number? Yeah. Does that mean all airplanes of this nature are going to go further? Not necessarily. We have a really small sample. Talk about all the airplanes in the world. Okay. I would probably, if I did this accurately, I probably would need some professional paper airplane builders come along. Right. And as we'll see later, we're going to do this test again. So save your airplane, or you can make a new one if you want. If you learned something about paper airplanes. X bar 1, 6.875. X bar 2, 4.125. S1, 5.71. S2, 2.9. 8, 8. We have everything we need to get our T statistic. Does that make sense? We can do it by hand and do a TCDF. We need a lower bound, upper bound, and degrees of freedom. Okay, once we get our T statistic, we can do TCDF. This is if you do it by hand. Even though you're using the calculator, that's considered doing the calculations by hand, because I mean, ultimately I could do that on my calculator on my cell phone. But we have this highly powerful calculator in front of us that does things that we never knew we were capable of doing. And it's called a two-sample t-test. It's called a two-sample t-test. I have two samples. We're comparing them. So let's do it. Stat, go ahead on your calculator. Stat test. Two-sample t-test, I believe, is number 3. Number 4, two-sample t-test. Oh yeah, number 3 is the Z. So number 4, two-sample t-test, press enter. And then do you have data or do you have stats? Well, we could do either one, but I'm just going to use the data because we already have it. So choose data. It's going to ask for your X list and your Y list. List 1 and list 2. There you go. Then it's going to ask for not equals, less than, greater than. We're going to choose a greater than. Do hot dogs go farther than hamburgers? Why do we need to know that? Because I need to know what is my T statistic and my P value. Yeah, because that P value helps us answer the question, helps us reject, helps us fail to reject. So what T and P value we get?
P value is 1.213. P value is 0.126.
Okay. Everybody agree?
We answered yes, right?
Are you pooling your data? Okay. So with this, when we have independent samples, if we pool our data, that means we're going to use the other standard deviation formula. So for this one, there's no pooling because the variances are not equal because they're different airplanes. They come from different populations. We got the hot dog population, we got the hamburger population. Their distances are going to be different. Their variations, their standard deviations are going to be different. So no pool. Good. Yeah. We are on to step 3. Now we can take our P value and make our rejection decision. P-value is low, reject HO. Like what's low? 0.05, that's a good number. P-value is greater than 0.05, we're going to fail to reject. HO, P-value. And if you saw the rubric on the quiz number 8, it's the same rubric that's on the test. It's the same rubric that's on quiz number 9. Quiz number 9 is 2-sample testing. 1 point for saying reject or fail to reject. 1 point for saying p-value is greater than 0.05. That's the Y. So some people missed that part, lost that point. And then the most important thing is we're going to answer the original question. Do hot dogs fly farther than hamburgers? Pretty much a yes/no question, right? Well, if I fail to reject, I'm pretty much saying there's no difference. That means there's no difference between these two numbers. Okay, but statistically, I can't say that. Statistically, we would say there's evidence of this, or we say there's not enough evidence of this. The hot dogs go farther than hamburgers. And that's what we conclude. Not enough evidence. Hot dogs go farther than hamburgers. So mathematically, you know, I could ask my children, they're little, which number is bigger, 6.8 or 4.1? You know, and they would all say, oh, that one's bigger, that one's better. Bigger is better, right? So 6.8. That's that's mathematically correct, but statistically, it's incorrect. That statement is incorrect. This number is not significantly bigger than that number. It's called a test of significance. We did not have enough evidence of a difference. Cool. 2-sample t-testing make a little bit more sense now. Or data, comparing 2 data sets. Okay, so I assigned, I believe, today 15 through 18. So we're going to do 8.2, 15 through 18. I'm going to give you about 30 minutes because I know you may be behind a little bit on homework or catch up or study or make note cards, or do whatever you need to do for the next 30 minutes to understand 2-sample testing. You could even go back and take your old quiz number 2 and, hey, I just learned something about testing. And now I know about p-value, and I'm going to go back and make my corrections on quiz number 2. You could do that right now as well. Or just take a break, go for a walk. To me, that's just extra work. You can do the extra work if you want to. You can follow the book to a T. You don't need me. Just use your book. Or you can just follow a 3-step process. That ask the question, answer the question. That's the goal of statistical testing. When you do a statistical test, you're trying to find, is there a difference or is there no difference? Is one bigger than the other? One less than the other? Okay, in the previous question, when we looked at the hot dogs and the hamburgers, I said, do hot dogs go farther? That was the question. I could have asked the same question like this. Do hamburgers fly shorter? It's the same question, isn't it? That makes sense? Okay, how's it gonna work? Well, then I have to switch these 2 things. This would be hamburger, would be hot dog. And I would say U1 is less than mu2. There we go. Hamburgers, their distance is less than the hot dog distance. In the end, we would get the same p-value. It would just be a left tail test we would get a negative P statistic. But it asks the same question, okay? I just want you to be aware of that because that's something that we'll use and pick up on when we're doing a t-test for dependent samples. Pretty common. All right. Are we ready for our rehash of paper airplanes? We're gonna do it again. This time we're going to do a paired experiment. We're gonna do a paired experiment, means you're gonna do two different things. You are going to build a hamburger airplane and a hot dog airplane. Okay? You're gonna build both. You're gonna throw both. We're going to measure the difference. Like I said earlier, if one goes 6 and the other one goes 6, the difference is 0. That means there's no difference for my airplane. But I'm gonna look at everybody's airplane. So again, if I throw the airplanes, I'm gonna come in here. Remember which is which. You might need to write on your airplane so you don't forget. If my hot dog, I throw it, it goes 10. I'm gonna write down 10. The hamburger, I'm going to say that goes 6. The difference is 4. Okay, so how are we doing this math? Okay, I'm going to do hot dogs minus hamburgers. I'm subtracting this way. I can subtract hamburgers minus the hot dogs. That would give me negative numbers. Negative numbers are less than 0. But when I do this, I'm going to call, yeah, I'll do new1 is dogs. new2 is burgers. Hamburgers. We're gonna modify the hypothesis slightly, okay? We're looking at the differences. So everyone's gonna throw 2 airplanes. And we're gonna measure the difference. Okay, that difference, if it's equals to 0, that means there's no difference. If it's greater than or less than 0, that means there is a difference. So we're looking at the differences, the total differences. So this is called mu d, or the book uses DIFF. That's mu1 minus u2. So I'm doing the dogs minus the hamburgers. I'm gonna write my hypothesis. Okay, we're no longer doing a 2-sample t-test. This is not a 2-sample t-test. 2-sample t-test means I got 2 different groups. Okay, like I said, I use the chemotherapy idea. We have 2 different independent samples. Now we're gonna do dependent samples. That means my sample sizes are gonna be the same. My hypothesis, I'm only gonna compare one thing. The mean difference. Is it greater than 0 or less than or equals to 0? Okay, one of my issues here is the calculation. X bar D, and this is going to be called SD for the difference. Okay, this is how we calculate, doing it by hand. We're not going to do this by hand necessarily, but it's a 1-sample t-test. Usually we'll see minus the mean, but the mean is going to be 0, so I don't even need that. Okay, in the book uses a symbol called D bar. The book creates a new symbol called D bar. We've been using X bar the whole semester for the mean, so I'm going to keep that. I'm just going to put a subscript D or diff for the difference. That's the mean difference. So I take all the differences and I find their average. That's the same as D bar. The book uses SD, and they create a whole entire new formula in the book. It's really weird. They create a new standard deviation formula. We have a standard deviation formula that we learned in chapter 2.4. When we were in 2.4 back in the day. Remember 2.4, we calculate standard deviation, we did it by hand, put data into a list, and we find the standard deviation. We're gonna find the standard deviation for all the differences, that's called SD. The formula is sum of x minus x bar squared over n minus 1. If you want to know where that new standard, some of you are going to go by the book. You can if you want to, or you can just find standard deviation on the calculator. This is silly. The book goes like this. You get the same exact results. And this is on page 439, I believe. We got a brand new formula. It's in the example 1. This formula is in the guidelines on page 438. This formula is in example 1. They give you a brand new formula, sum of d squared minus sum of d squared over n all over n minus 1. Okay, I would say what I did in my book, they come out to the same thing. They come out to the same thing. Why do we need to find the differences? All these are differences. I'm going to square each one of these numbers. Each of these is d. I'm going to square all those numbers, that's d squared. Then I'm going to find the sum of all those differences and square those. That's the sum of d squared, which are two different things. What a mess. I highly recommend not to do that. Don't do that. So there's extra work. You can do extra work if you want to. You can copy the book. You go to slater.com and register and they'll give it to you in the website. Okay. The calculator does it for us. This is called a t-test. In a t-test, it's number 2. Okay, number 1 was a z-test. Number 2 is d-test. What is the difference between a t-test for one sample and a t-test for the mean difference? These numbers here are going to be our numbers we're going to measure. If those numbers add up to be 0, that means that there's no difference. That means they go 0 feet, there's no difference. If the difference is positive numbers are greater than 0, that means there is a difference. If we get a negative, that means one goes less than the other. Okay, it's kind of hard to wrap your brain around until you actually do this lab experiment. Okay, if you can't, I'm running short of paper here, but you can keep your old airplane. If you were number 1 last time, keep your number 1 airplane and fold the number 2 airplane. You're going to throw 2 airplanes, a number 1 and a number 2. Okay. If you need more paper, there's more paper here. You're going to throw number 1 and number 2. You're going to measure how far each of those airplanes go. And you're going to write both measurements up here. You don't have to find the difference. I can do that. I can do the math for you. But we're going to do the calculations from there. All right, so we're going to spend some time right now measuring how far they go. So go ahead and grab paper and make your other airplane. And then we'll go throw them. We're going to throw both.
Thank you, Professor.
Thank you. All right. I've muted them out. So I could do the shortcut on the calculator, put all these values in the list 1. So I'm going to go list 1 right here. List 1. Put all these values in the list 2. So let's do that. Let's take about 2 or 3 minutes. Enter these numbers for list 1. Enter those numbers for list 2. Make sure you're entering data correctly. Just clear list 1. Everybody got list one, list two filled? Okay. Now I'm gonna find the differences. Instead of doing this by hand and writing down all those numbers, our calculator will do it for us. In list three, we're gonna highlight list three and say list three is list one minus list two. I want to need to subtract list one and list two. I could do list two minus list one. Subtract these numbers from those numbers. That's if I think there's a negative difference. But I'm going to do L3 equals L1 minus L2. Once I do that, list three should populate with all these numbers. I should not get an error. You got an error is because you did not highlight list three. Make sure you highlight L3. That will give you these values. Does everybody see those values? Yeah, we good? Let me know if you have an error or any issues. Okay. What do I need in order to do the calculation? I need the mean of those numbers. I need the standard deviation for those numbers. I'm not asking you to do it by hand. I'm asking you to enter those numbers in the list. Well, we already did. Let's find the mean and the standard deviation for that list. So we're gonna do that. Out. CALC. We're gonna do one variable stats. But make sure not one variable stats for list one, not one variable stats for list two, but one variable stats for list three. Make sure you choose list three as your list of data. Cool? Make sense? All right, now what I want to know is the mean difference. If that mean is greater than 0, that means there's a difference. Greater than 0. So did anybody get the mean difference? Shout out if you can.
0.72.
7.2.
0.72.
0.72. Holy cow, that's a really small difference. And standard deviation,
4.5.
pretty large spread. Okay. The difference is close to 1. That's a pretty small difference. I was thinking numbers like this. There was only a couple people. The hot dog went 12 feet. The hamburger went 4 feet. I was expecting a lot of this stuff. But look at all the negative numbers. The hamburger fold went farther. Okay. And again, because none of us are professional paper airplane makers, we're not very good at it, right? So that could factor into the reason why there's not much of a difference. What do statistics say though? Why do we do that? 0.75 over 4.5 divided by the square root of 18. That'll give me my T statistic. A number close to 0 tells me there's no difference. A number like above 2, 3, or 4, that means there is a difference. I usually do, some people made a mistake on quiz number 8 because you try to do the math here on your calculator and you ran into errors, okay? I usually do the denominator first and do 0.75 divided by, or 0.72, sorry, 0.72 divided by that answer. I imagine we're gonna get a T like around 1, something like that. Probably less than 1. Our T statistic. It'll give us a p-value. Our p-value is probably going to be rather large. We use a TCDF, like I mentioned the other day. We do a TCDF to get our value, our p-value. Okay, all that's fine today. That's all. So doing the work by hand. Calculator will do it for us. This is not a 2-sample t-test. We just did a 2-sample t-test. This is called a t-test. Or in other words, a t-test for the mean difference. So I'm looking for a t statistic and a p-value. Let's do it. On your calculator, press stat. Go to test. We have data. This is the data. So we're gonna choose data. Where is our data list? Our data list is L3 now. We're gonna use this data. We don't care about, we're done with, we just use that information. Now we're working on list 3. Not equals, less than, greater than. We're gonna choose greater than. Are these numbers greater than 0? Calculate.
You said just t-test, right?
Yeah, it's just a t-test. If we could do a 2-sample t-test with list 1 and list 2. We get a little bit different results. A paired test, a paired t-test is stronger than a 2-sample t-test. Stronger, meaning there's more evidence. It's a stronger test if we do a paired test. Okay, so I'm looking for a t and a p-value. Anybody get that? T and p-value, what'd you get?
T-value is 0.002. And the p-value is 0.499.
All right. Not much of a difference. Okay, a t-score close to 0 tells us there's really no difference between the two distances. Bless you. T-score of like 2, 3, 4. That means there is a difference. That means there's a great difference between these two values. Okay, so what's the conclusion? The conclusion is the same thing we did in chapter 7. 1, 2, 3, and 4. Same thing we're doing now in chapter 8. 1, 2, 3, and 4. We're going to reject or fail to reject. Looks like it's a fail. Just like we did with the 2-sample test, we failed to reject previously. Why? P-value is less than, or I'm sorry, is greater than 0.05. What's the answer to the question? Do we have evidence that hot dogs fly farther than hamburgers? No. There is not enough evidence. That's a no. There is not enough evidence. Hot dogs go farther. Our statistics told us there's no difference, really. No difference between these two things. But statistically, we don't answer it that way. We answer it, there's not enough evidence that there is a difference. There's not enough evidence that these go farther. Again, like I did with the 2-sample test, I could have reversed everything. I could have switched these two and chose a less than. Okay, greater than 0 is positive. I got a positive statistic. If I do a less than 0 test, I would do, this is list 1 and this is list 2, do a list 1 minus list 2, or I would do a list 3 is list 2 minus list 1. I'm going to subtract these two numbers. I'm going to get a negative. My mean difference would be negative 0.72. My t statistic would be negative 0.002, and I get the same p-value. We end up with the same results if I do a left tail test. We get the same p-value, but the test is a little bit different. Okay, so you can choose either method. Now here's the trick. Okay, all this is fine and dandy, but then it's tricky because what a lot of students will do is they'll just go, I'm going to do this minus that. They just look at the data and not the question. But then the question screws this up. The question would be like, do hamburgers go farther than hot dogs? Well, then I'm going to call this list 1 and this list 2. So how you name your data is really important. Let's look at an example of this. Okay, I'm just going to go straight to the problem sets because they're all page 442 through 445. Just take a look at these real quick. Look at 442 through 445. You see how they're all tables? 442. 445. We're gonna do 10 through 20 even. Ten through 20 even, 6 problems. Okay, but here's the trick. Looking at number 10, I'm just gonna help you through each of these. I'm gonna talk you through it. So you get an idea in your brain where the hang up is going to be. Okay. Problem 10. SAT scores. An instructor for an SAT prep course claims the course will improve test scores. Like I said, of course it should. Take the SAT first time. Get a terrible score. Go take a practice course to prepare for the SAT. You're probably going to do better the second time, right? Our scores should be higher. Did our scores improve? The table shows critical reading scores for 10 students on the SAT. Is there enough evidence to support the claim? So is there an improvement? Is the difference greater than 0? That to me, improved means greater. That makes sense? So the first time you take the test are going to be low scores. Does that make sense? The second time you take the test are going to be higher scores. Look at person number 1. They scored a 300 the first time they took the test. Second time they got a 400. If I do 300 minus 400, I get a negative 100. Does that make sense? I get negative numbers. But improving means greater than. Okay, I'm thinking this. This is what the question is referring to. I want the difference to be greater than 0. If you follow the book and go to Slater.com and you look up the answers and you use some help and you get a tutor, they're going to use less than 0. Why? Because they want to know, are the first time you take the SAT, are those scores less than the second time you take the SAT? Okay, I like positive numbers. I like to answer the question. So the question is, does the course help improve your SAT score? So what I'm going to do on this problem, this problem number 10. Problem number 10. I'm going to ask the question, does the course improve SAT score? Okay, that's the question. Is the mean difference greater than 0? Okay, any number greater than 0, give me a number bigger than 0. Any number. 2 is bigger than 0. It's positive. 2 is positive. Give me a number less than 0. Negative 1. Negative numbers are less than 0. Positive numbers are greater than 0. That's all I was asking for. Okay. So I want numbers bigger than 0. If I'm improving, means greater. So my data has to match that question. So in my data, I need the second time they take the test, those numbers to be greater than the first time you take the test. So I need 400 to come first, then 300 to come second. The difference is going to be positive 100. So how you enter your data is really important. The second time you take the test, I'm going to call that list 1. The first time I take the test, I'm going to call that list 2. I want to do a list 1 minus list 2. Okay. Or a lot of students will do this. Okay, this is common. I'm looking at the problem. List 1, 300, 450, 350. I'm just going to start entering data. A lot of people do this. I just enter the data into list 1. The first data that I see is list 1. Second data is list 2. Well, if I do that and I subtract, I'm going to have to do L2 minus L1. Okay, list 2 minus list 1. Because I'm looking for positive numbers. all my differences should be bigger than 0. If you do a left tail test or a right tail test, you should look at these numbers to make sure they match. If they don't match, then I got a mismatch. And that's all I write on for my feedback when you take the quiz or the test, you got a mismatch. Okay, you mismatch your data and your hypothesis. So if my differences are positive, in my data, then my hypothesis is greater than 0. Okay, so that's problem number 10. Problem number 12, batting averages. A coach claims the baseball clinic will help players raise their batting averages. Well, I hope so. If I'm a baseball player and I go to a batting clinic, I hope I get better. My batting average should improve. Is there enough evidence to support the coach's claim? Same exact problem. If they improve their batting averages, if I go into a clinic, then my data in list 2, the batting average after the clinic, should be bigger than the data in list 1. Now, one player got worse. Player number 4, their batting average went down. That makes sense also. The coach or the clinic messed up their batting. You know, when you're trying to hit a baseball, oh, put your elbow up, lean forward, put your left foot back. That just screws people up sometimes in sports, right? Doing too much. So sometimes you go down. It's understandable. There's 2 lists starting on problem number 11, problem number 12. There's 2 lists. Okay. All that data goes together. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. There's 14 players that attended the clinic. Okay, so you're going to enter the data. You're going to have 14 values that you're going to enter. Problem 14, grip strength. Does vitamin C help increase muscular endurance? Again, increase. Greater. So far, we're on 10, 11, and 12. And the hypothesis is going to be the same for all 3 of these problems. If you look at the answers, they don't do it that way. I got the answer here for problem number 14. They say the difference is less than 0. Okay, that's pretty lame because it says, does it increase endurance? I'm looking for taking vitamin C. Are those numbers using a placebo and taking vitamin C? Is there a difference? Is one set of data greater than the other set of data? Body fat percentage. A trainer claims high intensity power training decreases body fat. Again, it should, but does it statistically? Is it significant? Before and after. Decrease. Okay, I'm thinking the words say decrease. I'm thinking less than. You have less body fat after you work out. So I'm thinking negative numbers. The bigger numbers minus the smaller numbers would be positive. So we're going to do the smaller numbers minus the bigger numbers. I'm looking for negative numbers for problem number 16. Does that help? I hope. This is pretty tough. Okay, 8.3, pretty tough stuff. Okay, it takes a while for you to wrap your brain around, but you gotta just attempt a few problems in order for it to make sense and sink in a little bit. Okay. 2 sample testing, a little easier, but again, we're just doing a t-test for data. We're finding the differences. Was there a question?
So for number 16 is the body fat percentage after list 1 is that list 2?
So if you're gonna do list 1 minus list 2, I would do the after is going to be list 1 and the before is going to be list 2. Yeah. Decreasing.
Yeah.
I want the smaller numbers to be list 1 and the bigger numbers to be list 2. For decrease. For increase, for improving, for greater than. I want the bigger numbers to be list 1 and the smaller numbers to be list 2. Because when I subtract list 1 minus list 2, I either get positive numbers or I get negative numbers overall. All right, great. And the last one is obstacle course. Did your times improve beginning to end? And you can see that most of these questions, you're gonna choose greater than or less than. There might be one where it said, is there a difference? That would be equals and not equals. In that case, it doesn't matter which way you subtract, because your p-value end up multiplying by 2. To get your p-value. So if you do an equals and not equals test, you don't have to care or worry about which way I'm subtracting, and am I gonna get this wrong, okay? All right, so let's go for it. Let's do 8.3. I wrote it right here. Page 442, 10 through 20 even. 6 problems. Much smaller problem set, yes. Number 10.
I didn't file 15002.
Okay. You got a different number? Okay.